Okay, so we'll start our investigation and we're going to lead in an introduction and a hypothesis. So, before you start your introduction, think about your audience. So, are you writing to people of your own age, or are you writing to a bunch of research scientists who know a lot about what you're doing? Well, obviously, you're writing to people your own age. Don't think about writing your paper to me or your science teacher. Think about writing it to a friend. So it's really good to do it for a friend because they could read it over for you and see if they understand it. So this is your audience. Think about the information you need to tell them so they can understand your investigation. So an introduction takes the two key ideas about your investigation out of the research question and explains them. So, for example, my research question would be, how does changing the temperature of a wire affect the resistance? Two key ideas there, temperature and resistance. Everything else I know how to change things, I know what a wire is, but I might not know what temperature is or what resistance is. So I take those two things out and I start to put our introduction together. So one could be, resistance is electrons within the wire hitting the atoms and the wire slowing down. Higher temperature makes atoms move faster as they gain more energy. So those are the two things I'm starting to explain them. It's not a very good introduction though. What I could do is add examples to show that I understand. I could add diagrams. I could explain the key words I'm using. What do I mean by energy? Does the person who's reading that know what I mean? And most importantly, it's missing references. If I'm not doing research, then it's not a very good introduction. I haven't looked for the science behind it, so I'm going to have to go and look for that. So two key ideas, and I'm going to use these ideas to make a really good introduction. When you're finished with your introduction, give it to that friend. Let them read over it. If it doesn't make sense, then possibly change something about it. Okay, so now that's a quick overview of the introduction. We've got our two key ideas explained. What are we going to do with them? Well, we're going to make a hypothesis, which is just a fancy word for prediction and explanation. So now we write the hypothesis. It's a scientifically explained prediction of what we think is going to happen. So, going back to that one we had before, I think that increasing the temp will increase the resistance. So I've put what I think is going to happen. If I increase this one, what do I think is going to happen to this one? If I change this one, what's going to happen to this one? Because I'm not just stating here. I'm not just saying it will do this. Knowledge and the marks for knowledge come from explaining why you think that. Why you think it is so much more important than just what you think. So, because the atoms are moving around more, so more electrons will hit them. So that's really simple explanation of why I think that, but it shows that I understand what's happening. Again, I can make it better by explaining why we think this, why we think that's going to happen, giving an example and including my references. References are so important. I must do some research. Once again, give it to someone to read. They can help make it better. If they don't understand what you've put, then go back and change it. This is a really good start to a paper. Good introduction, good hypothesis, and then you'll know what you're doing as you go through the method. And once you get to the conclusion, you should already know what's happened, and it'll make it easier. See the video on concluding and evaluating for more information on that. Okay, now is time absolute. Absolute means, is it the same for everybody, no matter where you're in the universe? So if I time something, does someone else in another galaxy time exactly the same thing? Do we get the same time on our stop clocks? Well, the problem is, have you ever been in a car and the car next to you is moving at exactly the same speed and it looks like you're both stationary? You're both not moving, but you just happen to be going at the same speed. We're going to watch that again because I just like that. Well, Newton said, well, what about space? Is space absolute? If he was on his bike and moving towards this lamp, and I tried to time that, would I get the same time if the lamp was moving towards him? If they were going at the same speed? Well, I should get exactly the same time. For the bike, for him to go to the lamppost, or the lamppost to go to him, should it take exactly the same time? But it doesn't matter when I'm getting my speed. If I'm on my bike and the lamp's moving towards me, it looks like the lamp is moving towards me, and I'm just moving towards the lamp. So it doesn't matter which one I time, either time for the lamp to get to me or time for the lamp to get me to from me to the lamp. It doesn't matter. It should be the same time. So space is not absolute then, because it doesn't matter whether the lamp moves towards me or I move towards the lamp. It should be exactly the same. So that should be exactly the same time as me moving towards it. It doesn't matter. So space is not absolute, because it doesn't matter which one moves, as long as one moves relative to the other. Because before, when they're moving side by side, how do you get the speeds? If I measured it relative to the car next to me, it looked like I wasn't moving. So I have to measure it relative to something else. So if I say, okay, space is an absolute, but time is. So I'm going to measure how long it takes for me in this car to move this distance. And then I can get my speed. That's okay. So there's no absolute space, but there was an absolute time according to Newton. But then this beam of light came along and they realized it was moving at 300 million meters per second. That's the speed of light. But if it moves at that speed, as we've just seen, it must be moving relative to something that's not moving in order for me to get how quickly it is moving. So do you know what? We're going to have to do some more research into light. So what they did, they had two beams of light, and this thing was an observer moving away. This is an observer moving towards it. Funky graphics. But no matter if this is moving towards and this moving away, do you know what? They actually measured the bit as being exactly the same time. Something was going on with light that Newton couldn't explain. He said it should be space is not absolute, but time should be absolute. So if they're moving different distances, the time measured should change. So this was very confusing for people. But it came out as being the same time. So what they did, using Newton, if this light goes from here, the two observers should measure the same time. But as space is not absolute, they would measure different distances. But using speed equals distance over time, the speed of light would be different from every observer, and that can't be right, because we know the speed of light is constant. So that's what Einstein did. He came along and said, time cannot be absolute as the speed of light cannot change. It is the thing against which we measure the speed of everything else in the universe. So when we were looking for, in the beginning, our problem of things moving relative to each other, now space is not absolute and time is not absolute, but the speed of light will always be the same. So we'll have to measure something against the speed of light. Because if you think about it, if I want to say something moving relative to me, I'm not moving at the moment, but I really am. I'm moving on a planet which is spinning round, which is then spinning around the sun, which is spinning around the outside of the galaxy, which the galaxy is moving. So I'm moving all the time, so I can't really say it's relative to me. So Einstein said the universal thing at rest, thing that I can measure stuff against, is light. Newton didn't get it right completely, but Einstein finished it off for us. Okay, that's absolute time and space.